two-dimensional applied force and friction. Now we'll solve problems where the applied force acts at an angle to the friction force, so they are not parallel or perpendicular with one another. So take the case of a box being pulled along the floor at an angle. First, we do a free body diagram. As you can see, the free body diagram is very similar, except that the applied force is at an angle. But now we have to ask, in which direction could the object accelerate? Then make one axis along that direction and the other one perpendicular. So what's the answer here? We assume that the acceleration will be along the regular x-axis because we're assuming that the box doesn't bounce up and down as it moves. Now we have to resolve that force applied into x and y components so they can be along our axes. Now that the force applied has been separated into components, we can work with our x and y directions separately. So we are ready to solve the problem. For our first example, we are going to find the acceleration of a box of mass 3 kilograms if the applied force is 20 newtons at a 37 degrees above the x-axis and the coefficient of kinetic friction is 0.2. For the x direction, we have F in the x direction minus force of friction equals ma. In the y direction, we have force in the y direction plus normal force minus mg equals 0. So let's solve the y-axis first. We need to find normal force. The normal force is equal to mg minus F in the y direction. So that's mg minus force applied times the sine of the angle. We're going to use this for our force of friction. So F in the x direction is force applied times the cosine of the angle minus the force of friction, which is mu, times the normal force. And the normal force is mg minus fa sine theta. That is equal to ma. A is equal to force applied cosine theta minus mu times mg minus force applied sine theta divided by m. Now let's plug in our numbers. So the force applied was 20 and the angle was 37 degrees. Mu is 0.2. M is 3 times G, which is 10, minus the force applied, which again is 20, times the sine of our angle, 37 degrees. That's all divided by m. Now A comes out to 16 minus 0.2 times 18 divided by 3. And that is 4.1 meters per second squared. Now let's compare the differences when you pull a wagon at an angle versus pulling it horizontally. So here's our two examples. Both have the same force applied, both have the same coefficient of friction, but one is horizontal and the other one is at an angle of 37 degrees from the horizontal. You can see when the box is pulled horizontally, the normal force is equal to the weight, 30 newtons. But when it's pulled at an angle, the normal force is less than the weight, 18 newtons. You can also see that the acceleration is greater when it's pulled at the horizontal rather than when it's pulled at an angle. Friction was reduced when the box was pulled at an angle because the normal force was reduced. You can see when just looking at the y-axis that the normal force plus the force applied in the y direction minus mg equals 0, so that the normal force is equal to mg minus the applied force in the y direction, making the normal force less than mg. Now that explains the difference in the normal force, but since the friction force is greater for the object pulled along the x-axis, why is its acceleration greater than the object pulled at an angle? That one's not as easy. It depends on the angle and the coefficient of friction. If you try solving the equations algebraically for the two cases, you should find that if cosine theta plus mu k sine theta is greater than 1, then the pulling the object at the angle results in a greater acceleration than if the force is aligned with the x-axis. If equal to 1, it's the same, and if less than 1, then a greater acceleration results from the force being horizontal. Instead of pulling the object at an angle, what would happen to the acceleration of the object if it was pushed along the floor by a downward angled force? What would happen to the normal force and the force of friction? So let's look at an example. Here's the free body diagram superimposed over the box. So we've got normal force up, mg down, force applied down and to the right, and force of friction to the left. Which do you think is going to be greater, the normal force or mg, or will they be equal? Since you're pushing on the box, the normal force is down, and also the y component of the force applied is down. So our sigma F equals ma would look like normal force minus force applied in the y direction minus mg equals 0. So that the normal force is equal to mg plus the force in the y direction, making the normal force greater than mg. So now let's look at the x-axis. We have the force applied in the x direction minus the force of friction equals ma. So the force applied in the x direction is F cosine theta, and the force of friction is greater than it would be normally. So the acceleration is equal to F cosine theta minus mu k times the quantity mg plus F sine theta, all divided by m. Now let's compare the two equations for the acceleration for a push and a pull. They are very similar, except for the normal force, and therefore the force of friction. For a push, we have mg plus F sine theta, and for a pull, we have mg minus F sine theta. Which one do you think would have the greater acceleration for the same force? For any given force, the acceleration pulling is always greater than pushing. So that's why it's easier to pull a lawnmower than it is to push it.